quiz, if you finish early, please stay. Don't disturb the other people getting in and out. Stay for 5 minutes. You like it. Just stay here if you finish early, and then everyone finish leave at the same time. If your whole row is everyone has finished, then you can leave. But otherwise, don't disturb other people. Please try to leave. All right, so we have 2 minutes for class. Anyone have any questions?
We put the grades right down.
Yes.
Are you gonna release the exam for us to like view our wrong answers?
Do what? The wrong answers?
Yeah, like to see like what we got wrong or right. Are we gonna be able to like see that?
No, but it's only 8 questions. If you remember the questions, we can talk about it.
No, not the quiz.
Exam one. For the midterm.
The
She's
midterm.
asking if we're being able to
The
view our
midterm,
midterm.
no.
Okay. That's fair.
Final is not converted. Final is not
I think
converted.
he's not interested.
So regarding any questions, I don't discuss any. I don't bring up any question from the exam. If you remember a question, you have want to ask me something. Questions have to come from you, not from me. So if you remember any question from the midterm, from anywhere else in the world, any question you want to ask, you can ask me, but the question has to come from you, not
How am I
from
going to
me.
remember 30 questions?
I'm gonna remember 30 that come.
I got 30 more. I have to remember.
That would help. You put X's in front
This is not like baby.
I know. Everyone says it like casually.
I like feel like X's. I actually
Yeah, actually. So it's been like, oh shit. One by four, no.
Just so you know. I just I get it.
Oh, you need it, right?
No. I needed the bigger one. That's why I was like, because that's the charge for camera.
There's no, yeah, there's no wiggle room. Oh, and that's oh my god, it's gonna die? That's needed.
No. It's alive. It's gonna stay for a while. It's just running on one battery.
That's like the reason I got like at least like 10 credits.
If I fail 1 year because of my camera, I'm changing majors.
Wait, because that's I get more
He's not gonna bring them back. So the thing is, he's not gonna bring them back. Because like the final phase, like cumulative.
No, he just said no.
It's bad. It's always said. It's like blatant subjects.
Yeah, I feel like
I
most of
never
them
bring in concepts from the first exam to apply to this exam. Like, he'll use like,
how many classes are there?
that's what didn't work.
But I swear, like, I wasn't mad about that. I was like, one
I
of
thought I was gonna get third.
yeah, that's
Not part of the 30
The
yet.
overall idea of making ATP is oxidize NADH and QH to have protons pumped from one side of
Make that one.
the other. You need a larger.
How do you share
It's not working.
All right, is it okay?
Oh my. I couldn't believe it. Oh, I can't hear you. What's wrong with me? Maybe my ears are bad. It's just
All right, you're farting too much.
okay.
All right, you can hear now. No, I'm close to that. I'm not close to that. So, the oxidation reactions release energy, and that energy is used to pump protons from one side of the membrane to the other. And the names of the two sides are the matrix inside the mitochondria to the intermembrane space, that means the space between the outer and inner membrane, which, as I mentioned, is similar to the cytosol because there is free movement of things. Now, there are two ways you can form a gradient. This was one way, that means use the delta G of the reaction, negative delta G to pump protons to the other side, and we saw that complex 1 and 3 and 4 use the energy to pump protons. Complex 2 doesn't because it has almost very similar delta G, the reduction potential, or the delta G is 0. So that doesn't contribute to the proton gradient. But what it does contribute is QH2. So complex 2 is the same as succinate dehydrogenase of the citric acid cycle, which is in the membrane, and it converts QH2, so QH2 will be oxidized to give you energy. So that's one way of forming a gradient. There is another way of forming a gradient, and that comes by balancing the equation. That means the stoichiometry of the reaction itself. For example, if you want to make Q, at first you want to make NADH in the various reactions that we have seen before, and also you want to make Q in the complex 2. Q is converted to QH2. Where is the hydrogen coming from? The hydrogen came from the succinate, right? So the succinate to the fumarate. So we form an alkene and the two hydrogens go to the QH2. Now the goal of this whole process is to increase the hydrogen on the intermembrane space side and decrease the hydrogen on the matrix side. That's how you create a gradient. And nature has evolved to have these reactions. Whenever a hydrogen is needed, that hydrogen will be taken from the matrix side, because that is the goal. You want to take hydrogen from the matrix side and transfer it to the other side. So if a reaction uses hydrogen from whatever source, here it is succinate, that enzyme will be facing the matrix. The active site of that enzyme will be facing the matrix, so that the hydrogen is taken from the matrix, and that way you decrease the number of hydrogens there. And when that hydrogen is no longer needed, that hydrogen will be released, and released as a proton. And where do you want to release it? You want to release it on the other side. So the enzymes will be facing for that particular reaction on the side of the intermembrane space. So the membrane has two sides, and the enzymes are appropriately positioned and facing so that it will decrease the hydrogen concentration on the matrix side and increase it on the intermembrane side. So this way, by following the stoichiometry of the reaction itself, you create a gradient. So if you have a membrane here, and you take a proton from this side and transfer it to this side, that is a one proton gradient. You have to take one from here and transfer to here. That creates a one proton gradient. If you take one proton from here and convert it to some molecule, let's say QH2. So you are converting this proton to something molecule that's not going to the other side, but you are decreasing on this side. Whatever reaction, I just wrote a reaction, but it can be any other reaction where a proton is consumed. So you're decreasing it on this side, so that contributes a gradient of half, right? Taking one from here to here is one gradient. Taking one from here and not going to the other side is half a gradient. Or there's another reaction that releases hydrogen from in that reaction. That hydrogen also will contribute half proton gradient. So the two together will add to the gradient. So for example, what happens to the QH2? It will go to the complex 3, and the QH2, so this is complex 3. QH2 will be converted back to Q, and the hydrogen will be transferred to something else. Usually the hydrogen is transferred to another molecule. For example, from NADH it was transferred to Q. From Q, where will it be transferred? The next oxidizing agent is cytochrome C. Cytochrome C is an oxidizing agent because it has a metal ion in its active site. It doesn't really bind to hydrogen to get reduced. So in cytochrome C, there is a ferric ion that goes to the ferrous side. So metal ions, when they get reduced, they don't need a hydrogen. So what will happen to this hydrogen? This hydrogen will be released as protons. And in these, we are studying it for only a few hours. Nature has worked with these for billions of years, and they have perfected this efficiently to use the proton gradient. So the enzymes are rightly positioned so that these protons that are no longer needed to reduce the iron will be released into the intermembrane side, and that way it contributes to the gradient also. So this way you contribute more protons to the proton gradient, either from consuming electrons on one side or consuming protons on one side or releasing protons on the other side.
So you said that half a gradient is made from H plus to QH2, and then
No, not a half a gradient. That didn't take the proton from it came from the molecule itself. And I'm just showing where the hydrogen came from. It didn't come, there was no H plus. It comes from the succinate, which is the formula of the molecule itself. Right? There is no H plus that is attached to the Q. So when it converts back to Q, this proton is released as H plus. So after this, then the cytochrome C, which is now in the reduced form, this goes to complex 4. And in complex 4, this is finally where the oxidation takes place by reacting with oxygen. And when you react with oxygen, what do you get? So that will combine with oxygen plus proton plus electron to give you water. It's not balanced, so if you want to balance it, you need 4 of these and 4 electrons. Right, so the idea here is that when it is reacting with oxygen, it is reacting with proton also to form water. And if proton is a reactant, where do you want that reactant to come from? We want it to come from the matrix side so that we decrease the number of protons there. Here we wanted to release these protons to the intermembrane space. This enzyme is facing the matrix side so that the proton is taken from the matrix side. So whenever proton is a reactant, the enzyme is facing this way. When it is released, it is facing the other way. And that way, this also contributes to the proton gradient because proton is being consumed from one side. So adding these up to put exact numbers on how much these complexes contribute will make mistakes there because every book tells different things. But everyone agrees on one thing, that the total at the end, 1 NADH gives you 10 proton gradients. So these are 10 proton gradients. That means you took 10 from one side and moved to 10 from the other side. So 1 NADH gives you 10 proton gradients. The QH2 comes from different sources, like it comes from complex 2, or it also comes from complex 1. So this was complex 2. In complex 1, remember the NADH is converted to NAD, and at the same time Q is converted to QH2. And in this case, again, there is a need for a proton, because NADH has 1 proton, QH2 has 2 protons, so that proton again comes from the matrix. So Q has 2 sources. It can come from NADH in complex 1, or it can come directly from complex 2 without going through complex 1. So how many protons gradient will complex 2 starting from complex 2 give? If you bypass complex 1, then complex 1 actually contributes 4. So every QH2 will give you the 6 proton gradient. Because the QH2 has bypassed complex 1 and entered directly from the citric acid cycle, so that will give you 6 instead of 10. Yes?
Does complex 1 contribute half of proton gradient?
By the formula, yes. But besides that, it releases a lot of energy and so it pumps protons.
But it also releases half a proton on the other side, right? So does it just cancel out?
So where does it release the proton? It's the proton that it has.
Like that drop right in the middle, is that complex 1?
No, this is just an example of how the proton gradient is clear. What a gradient is. This is not about complex 1.
Okay.
What is meaning of a gradient?
Okay.
So complex 1, so all of these don't try to pinpoint exactly how many protons because books even don't agree. Just try to understand the concept that this is how the gradients are made. But at the end, it will be 10 protons per NADH and 6 proton gradients per QH2. And to make ATP, all these protons will have to go through complex 5, so there will be a complex 5 here. And protons go from this side to this side, and then the process it makes ATP. And the calculation is it takes 4 proton gradient to make 1 ATP. So 4 protons have to come through this machinery. So this is complex 5, which is ATP synthase. It's an enzyme. As the protons go, that energy is used to make ATP. So 4 protons make 1 ATP. That means for NADH, 10 divided by 4 will be 2.5 ATP per NADH. And QH2 will give you less because it has bypassed the complex 1, so this gives you 6 divided by 4, so that's 1.5 ATP per QH2. So this is also called the PO ratio. So remember this whole process is called oxidative phosphorylation. You are oxidizing something and phosphorylating something. So how many oxidation gives you how many ATP? That is called the PO ratio. Phosphorylation to oxidation ratio, and so these numbers here are the PO ratio. So PO ratio for NADH is 2.5, for QH2 is 1.5, and these are the numbers that people didn't agree on before. People thought you cannot get a fraction and a number because how can you do a chemical reaction with half a molecule, but now we know that it's not the molecule, it's the proton that is giving you ATP, and that's where these fraction numbers come from, and so these are the PO ratios for QH2 and NADH. All right, so when this reaction, as I said, this is ATP synthase in complex 5. That will use ADP plus phosphate to make ATP. This reaction is actually an equilibrium reaction, and delta G for this is about 0. So that means when ATP synthase carries out this reaction, it doesn't really require energy to do the reaction. The energy is needed to, so if this is the enzyme, ATP is tightly bound to enzyme. At the end of the reaction, the ATP is tightly bound to the enzyme, and in order to release it from that enzyme, you need all these protons. So the reaction happens as an equilibrium, but as the proton moves through the ATP synthase complex, this ATP is released from this enzyme, so the enzyme is free, and then it catalyzes one more reaction. So it takes 3 protons to release the ATP. All right, so no energy is needed for the reaction itself, but the energy is needed to move the reaction forward by releasing the product so that it can catalyze another reaction. So this is 3 protons per ATP, but I said there that is actually 4 protons per ATP. So where is the 4th proton coming from? 4th proton is coming from balancing this equation. To balance the equation, you need a proton. So you have, this is the intermembrane space. So let's say cytosol and matrix. And through complex 5, the phosphate has to come in, the ADP has to come in, and when you make ATP, the ATP has to go out because the matrix has no need for that ATP. It has to send it to the rest of the cell or the rest of the body. So it has to be exported. So ATP has to go out, phosphate has to come in, ADP has to come in. And we already know the structures of these. How many charges are there in ATP? There are 4 minus charges. ADP has 3 minus charges. And phosphate has 2 minus charges. So you are bringing in 5 minus charges and bringing out 4 minus charges. So there will be a charge imbalance. That cannot happen. So to balance that charge, or also if you write the equation, this equation, if you write, there will be need for a proton, so another proton has to be brought in along with this. So proton also comes in. So proton, phosphate, ADP, all 3 come, ATP goes out, and that way you bring in 4 charges, 4 minus charges, and 4 plus the minus charges go out. So that way the charge is balanced, and this is where the 4th proton is. So 3 protons are needed to dislodge the product, 1 proton is needed to bring the reactants into the mitochondria and export the product, which is ATP, out of the mitochondria.
So you need the 3 protons to separate the ATP from the enzyme?
Right. And the 4th proton is basically to balance the equation. So that's where the number 4 comes from. It takes 4 protons to make 1 ATP. Now, all these numbers that I gave you, the PO ratios, these are the optimum efficiency of the cell. It doesn't mean the cell is always functioning at this optimum efficiency. It may be less than that. If it is less than that, then it means that there is some proton that is dissipated without making ATP. So the protons are brought from one side to the other. If it comes from any broken parts, but not through ATP synthase, then this type of a transport of protons will give you less PO ratio for both of them. The question is, does this happen? Why would the cell have a broken mitochondria? Actually, it doesn't. It never has a broken mitochondria that protons can go in through that. But then there is actually some leakage. So this is called a leakage. There is actually some leakage deliberately. As I said, there's nothing inefficient about the cell. Whatever happens, happens for a reason. And these leakages are already designed to bring a proton to the other side. And there is actually a protein that brings it in. So it's not just coming through broken pieces of the membrane. There is a protein here called thermogenin. And from this name, thermogenin, you can expect why this protein is there. This protein is there so that the proton comes in and that energy is released to release heat. So who needs the heat energy? For example, all the animals that hibernate in winter, they need the heat energy. So they have these in large amount to bring the proton without actually making ATP or without doing mechanical work. They still need to generate energy, so there is a certain percentage of proton gradient that is released this way, maybe about 20% or so when they are hibernating. Humans also have these thermogenins, and which human needs this? This is not a weight loss drug, it's most needed by infants. Right, so infants don't do any work, right? They're just lying there all the time, but they are the fastest growing compared to the adults. So they need a lot of energy, although they are not doing much activity, just throwing their legs this way and that way. So they need to generate energy, so they have a lot of this happening And more of this happens when there is more mitochondria. And mitochondria has iron in it, as I said, cytochrome C has iron, and so mitochondria gives it a slightly brown color. They call it brown adipose tissue. So infants have brown adipose tissue, usually in the back of the neck or backside where they generate more heat. It's called brown, but when you look at it, it's not really brown, it's just off-white. And the color is because they have a high concentration of mitochondria and there's lots of these thermogenesis that are releasing energy just by dissipating the radicals. All right, so with all that information, there is one information that is missing here, and that is the NADH that you made in glycolysis. Where was that NADH made? In the cytosol. And where is all this oxidation happening? In the mitochondria. So how does the NADH of the cytosol end up in the mitochondria to get oxidized? In fact, they don't, and that was the whole reason, and this was a question in one of the quiz, I think. Why is pyruvate converted to lactate? Just that because to make the NAD, and all the NAD is used up, the cell cannot carry out glycolysis anymore, so they have to convert pyruvate to lactate to make more NAD. So that means the NAD cannot cross the membrane. The NAD is written with NAD plus, and that is very confusing, and actually the plus sign is basically wrong, but still everyone writes it that way, NAD plus. What is the charge of NAD? So NAD is actually negatively charged because it has phosphate in it, right? The phosphate has negative charge. One of the carbons have a positive charge, and that's why it's written as NAD plus, but it is actually negatively charged. Overall negative. So whatever the charge is, charged things don't go through the membrane, so NAD of the cytosol will never go to the membrane, go through the membrane to the mitochondria, but it needs to be oxidized. Because the pyruvate to lactate happens in absence of oxygen. In presence of oxygen, that NADH is oxidized, even though it doesn't cross the membrane. So how does it get oxidized then? There are two pathways that are used, and we are not going into the details of the pathways. One is called the glycerol phosphate shuttle. One is called the glycerol phosphate shuttle. The other is called malate aspartate shuttle. And in both these cases, the NADH is never really transported because NADH cannot go through the membrane, but the reducing power of NADH, in that hydrogen, is transferred to another molecule, and that is transported to the other side to be oxidized. So without going through all the steps of this, for this one, if you have the membrane here, and let's say this is the cytosol, and this is the matrix. So the NADH will be converted to NAD by an enzyme on the membrane. And the name of the enzyme, of course, will be related to glycerol, because it will convert glycerol to dihydroxyacetylphosphate, but we are not going into that reaction, but basically it is a reduction reaction. So, and that will have a coenzyme, and that coenzyme is FAD. So FAD, as NADH goes to NAD, the hydrogen is transferred to FAD. And FAD, as you know, is a prosthetic group. It never leaves the enzyme, so it must transfer it to something else. And that something else is, I should be drawing the membrane bigger, so this is all happening in the membrane. And then the FAD is converted back, FADH is converted back to FAD, and the hydrogens are transported. So you are not transporting the NADH to the other side, you are taking this hydrogen, putting it on the FAD and then on the QAC. So you are converting NADH basically to QH2 without directly reacting with it, but going through that intermediate enzyme. So that's why this is called the glycerol phosphate shuttle. And you actually sacrifice something by doing this, because NADH is supposed to give you 2.5 ATP, and QH2 gives you 1.5 ATP. Right, so if you are very strict about calculating how much ATP you get for NADH, you have to think that the cytosolic NADH will not give you 2.5, it will give you 1.5. If it uses this shuttle is mainly used by lower organisms like insects, because this is very fast, and so they need the energy very fast, and they use this. Higher organisms also have that, but they also use the malate aspartate shuttle. Again, this is a complex series of reactions that happen, but the whole idea here is that the NADH will transfer its hydrogen to, so as NADH in the cytosol is converted to NAD, the hydrogen goes from oxaloacetate to malate. So this hydrogen is transferred to oxaloacetate to make malate, and then there is a transporter on the membrane. So this is happening in the cytosol side and the matrix side. So there is a transporter that will transport the malate to the site. So basically, the proton of NADH is transferred to oxaloacetate, that becomes malate, and then the malate will be converted back to oxaloacetate, and a proton will be added to NADH. So you are not really transporting the protons, the NADH, you are transporting the hydrogen and making NADH here. And then the oxaloacetate, of course, has to come back here to complete the cycle. So this is called the malate aspartate shuttle. The idea here is to transport the proton of NADH to the other side. And once again, if you want to balance this equation, you will find that every time it is doing this, it needs a proton here, so NAD plus a proton, and this will release a proton in this reaction. So one proton is taken from the matrix side and is transported to the outside. No, I mean, right. It's a very, you need you need a proton here, because you need two protons. So one from here, which add to oxaloacetate to make the malate, and you need the malate. When it goes to oxaloacetate, it will make one proton. So one malate will have two protons. One goes to the oxaloacetate, and then it releases a proton. So basically, taking a proton from one side and releasing it to the other side, you are instead of a 10 proton gradient, you are getting a 9 proton gradient. One proton is in the formula for that equation. So to be calculating very strictly, you are actually making 9 proton gradients instead of 10, and that's why you don't get the full 0.5. You may be getting 0.25 from these reactions. Yes, I will be back in a minute. All right, so that's the last thing in this chapter. Let's do it next class. There is one proton to balance the equation. because we need to go to the courts. So we will, so this was the last thing, we will end with this also in the last next class. And,
Transferring NADH from the cytosol into
no, they're transferring the item. Renegade case is, Renegade doesn't work. You're transferring it as a manual.